of non-volatile solute particles and not the chemical nature of these particles. Okay, you only look at the number of those non-volatile particles, but you don't look at the chemical nature of these properties. Okay, so as well we looked at these properties. We said, one, we have vapor pressure lowering of the solvent. Two, we have boiling point elevation of the solution. If you can look at the slide. Freezing point depression of the solution. Also we have osmosis and osmotic pressure of the solutions. Okay, those are the four properties we have been looking at. Previously we looked at vapor pressure lowering, looked at boiling point elevation. Yesterday we looked at freezing point depression. Today we are going to look at that the fourth colligative property. For this case we are going to look at only four. That is going to be osmosis and osmotic pressure. And we said that these properties can be used to determine the relative molecular mass of a solute in a solution. Okay, and you have been doing so. Okay, so today allow me introduce to you that osmosis and osmotic pressure, and we dig deep into details of it. Okay, so what is osmosis? I understand that you did some biology in O level. Okay, and you looked at this term. As well, you did chemistry in O level. In senior one, you look at osmosis. Okay, so today we are back with osmosis, and we are saying is the movement of solvent molecules from a dilute solution to a more concentrated solution through a semi-permeable membrane. When defining the term osmosis, okay, when defining the term osmosis, there are key terms that you should not miss out. Movement from a dilute solution to a more concentrated solution through this. That is, we have to apply semi-permeable membrane. The word semi-permeable membrane is very important in that definition. If you don't talk about it, you are going to miss out on the mark for that definition. So you should make sure that you talk about the word semi-permeable membrane, and you emphasize that there is movement of molecules from the dilute solution to a more concentrated solution, or from a solvent to the solute side. Okay, so we can also look at osmotic pressure. This is osmosis. Now let us look at osmotic pressure. What is it? Back to our slide. Is the mechanical pressure which must be applied on a solution to prevent passage of solvent molecules into the solution through a semi-permeable membrane. This one, osmosis, is the movement, okay? But osmotic pressure, is the pressure that is trying to curb that movement of solvent molecules, the crossing of the solvent molecules. With them, we are going to see how important it is to block molecules from moving, okay? To block these solvent molecules from moving. So, solutions with the same osmotic pressure at the same temperature, they are termed to be isotonic solutions. The word isotonic is only applying for those molecules which have the same osmotic pressure at the same temperature. Okay? So, other terms that people look at, we have hypertonic solutions, hypotonic solutions, but for this case, we are not going to go far. That is more of biology. Let us look at the importances of osmosis and osmotic pressure. Those are the importances. You well know that when we are dealing with chemistry, we talk about osmosis, how it is applied in chemistry. But as well, when you go to importances, you can generalize and say now there is uptake of water by plants through the roots. It is used in determination. For this case, we are using it for determination of relative molecular mass of polymers. Okay, and in most cases, in some cases, it is used in many biological processes like distribution of nutrients, release of metabolic waste products within our body. Okay, that's why I said this is more of biology. However, these science subjects work hand in hand. You can cover something in chemistry as well as you also cover it in biology. It is of no harm. Okay. So when we move next, we are going to look at what they call an experiment. Okay, used to determine osmotic pressure of the solution. Okay, that is the diagram we can look at that we are going to use to explain more of osmotic pressure. In chemistry, if you want to understand most of the experiments, first put a diagram into your head. Once you put a diagram into your head, everything will be fine. Okay, once you know the diagram, you know how to label it, then you can talk about it. When they say describe an experiment, just draw a diagram on the side and now start looking at it. You pick apparatus from the diagram. You pick the procedures from the diagram. You look at the diagram and you see what comes first, okay, and what comes last. You pick the illustration from it. Even you pick the conclusion from it and the observation, okay. So once you have a diagram, you are powerful. You have everything, okay. So let us only focus at that diagram and describe a number of things, okay. When you look at that diagram, you can see that there is up, is where pressure is applied from. You have the pressure gauge, you have the piston, okay? The piston is for opening and closing. And it is helping to regulate the amount of pressure entering, okay? Capillary tube, you have the reservoir, you have the tap, the solvent. You see where it is. You have the solution. You can see the solvent is within the cylindrical tube, and the solution is within the steel vessel. Okay, the solution is within the steel vessel. That arrow going down is having a steel vessel. Okay, then you can see the semi-permeable membrane where it is. Okay, I said whatever you want to do, the procedure that you want, just let us focus at that diagram and describe the procedure that can be followed. Okay, what you need is you get a solution whose osmotic pressure you want to obtain. Okay, you put it in that steel vessel. That arrow going down, that big thing is the steel vessel. Okay, you put there the solution of which you want to determine the osmotic pressure. Okay, then you separate that solution from the solvent using a cylinder. So you put the solvent within that cylinder, which has a semi-permeable membrane. Okay, once you do that, then the solvent molecules, we are still on that diagram. The solvent molecules will flow through that semi-permeable membrane. Okay, where is the semi-permeable membrane? And you are seeing the solvent in the middle. So the solvent will flow from that middle part to occupy where there is the solution. Remember, we have said that osmosis is the movement of solvent molecules from a dilute solution into a more concentrated solution. Okay, so where there is a solvent alone, we term that to be very dilute. Okay, you may find it has very few solute particles, but where there is a solution, we assume that there are so many solute particles, so it is a concentrated solution. Okay, so once you have set up the experiment, the solvent will start to flow from where it is into the solution. Okay, and to the solution, there you see it will force the solvent levels in the capillary tube to fall slowly. In that capillary tube, you see where the capillary tube is, you will see that capillary tube, the solvent going down. That means there is loss of the solvent in the cylindrical tube. Okay? Please, I've said that we are going to use that diagram to explain everything. Okay? We have used the definition, we have used the diagram, and we are still saying that the tendency of the solvent molecules to pass into the solution is balanced by pressing the piston. You can see the piston up. Okay? Just for you to balance the tendency of those solvent molecules, not to move very fast, not to move very slowly, okay, but to move at a steady speed. You have to press the piston. And when the solvent in the capillary tube is just at equilibrium, there is no more solvent molecules passing through the membrane to the side of the solution. Okay? So we say that now there is equilibrium. If solvent molecules are not moving from the solvent side into the solution part, we say now that we have gained equilibrium, and the pressure at this point is the osmotic pressure. The pressure balancing the movement of solvent molecule is what we call the osmotic pressure. Because we have said that osmotic pressure is the pressure that is used to block the movement of solvent molecules from a region of low concentration of the solute to a region of high concentration of the solute. Note my words very well. Then some of you might say that now you are talking much. I don't want a level student to get content in a similar way to an O-level student, okay? Because for you at least you have light about these things. So let us do much of explanation. Slides are there. You'll be doing some writings, okay? But where necessary, take note of these things, okay? Then we see that in the steel vessel, it is direct. You read the osmotic pressure from the pressure gauge. If you can go back to the diagram, there is a pressure gauge on the right hand side, okay? You can see the pressure gauge. It's where you read the osmotic pressure from, okay? We have said that everything is on that diagram that you can talk about. Then the osmotic pressure is more accurately determined by taking the average readings, okay? Take note of that. It is more determined by taking the average readings on the gauge when the levels are slowly rising and falling, as it is difficult to adjust the pressure to exactly attain the equilibrium for no movement of either sides. So in that, when you are trying to maintain a constant flow, it is very difficult for you to say that no solvent molecule is going to move from the cylindrical tube into the solution side, okay? That one is very hard. So what you can do is that you keep taking values and you get average. You see values which are close to one another, then you take average of them. So within that, we can experience what they call the reverse osmosis. What is the reverse osmosis? This is the movement of water from the solution side to the solvent through the semi-permeable membrane on application of too large pressure on the solution side of the membrane. Okay, so our major focus was movement of solvent molecules from the cylindrical vessel into the solution side. Okay, but now we are seeing that even there can be movement of the solvent molecule from the solution side into the cylindrical tube where there is the solvent only. And when that one happens, we term that one to be the reverse osmosis. So when in the exam they ask for define the term reverse osmosis, or what do you know about it, or write short notes about the following terms, and they give you reverse osmosis. So you should be able to define it. Don't define reverse osmosis as you start with the words like opposite movement. People will not understand that, okay? Define it in a proper way. Movement of water from the solution side to the solvent through this impermeable membrane, okay? When too much pressure is applied on the solution side, okay? And you can see that the solution is also in the same, you can see pressure is coming from up, meeting the solution first, okay? So it is pressing both, okay? So you should, the pressure exerted should not exceed the limit. If it exceeds the limit, that means it will go into reverse osmosis. I think that has been very wonderful, okay? And everyone has taken note of it. So we can move to our slide next, and we see all what we have been talking about. You'll be able to access these slides and rate, okay? You rate. But what I've talked about, a student who knows what he wants, he or she, what he wants, okay? You have been able to rate something, okay? You have been able to note, or you have been able to learn how to do things, okay? So on our next slide, you see the procedure that we are talking about, okay? Let us see the procedure that we are talking about. When you get the procedures, don't cram them. Just you read, okay? You read how they are, and you use them you phrase them in your own language or in your own understanding. When you go to our next slide, we also see the same. Then next, that is what you have been talking about. You will be able to write. Then we go to our next slide. That is the reverse osmosis. Then we go to now factors affecting osmotic pressure or you can call that one laws of osmotic pressure. We have concentration, we have temperature. When we move to our next slide, you see we are going now to begin with concentration. Okay? Concentration. You realize that concentration is directly proportional to osmotic pressure. And when we are describing it, we say osmotic pressure of a dilute solution is directly proportional to the molar concentration of the solution at a constant temperature. We'll look at that on our next slide. Okay? Then we say, why is it directly proportional to the molar concentration of the solution at a constant temperature? We realize that it is because the concentration of the solution will be high. When it is high, when the concentration of the solution is high, the movement of solvent molecules from the side of the solvent to the solution through a impermeable membrane will increase. Okay? Once the concentration at the other side of the solution is high, there will be a fast movement of solvent molecules into that side. Okay? And the reverse is true. And that means when it is low, that means also there will be a decreased rate of movement of the solvent molecules. Okay? Therefore, once there is high and increased movement, we shall say that also it will require a high osmotic pressure to be applied to force back the solvent molecules. Okay? So the also osmotic pressure will be high. Right? That is it. However, when you go to the next slide, you're going, whatever we do, we may talk about very many words, but we have to put them into the calculation side. We see how can we apply those words into the calculation part. You see that that side is the proportional, it represents the word directly proportional. It is a proportionality sign. So pi is representing osmotic pressure. So we say pi, which is osmotic pressure, is directly proportional to concentration of solution C. Then you'll be able to say pi, then you remove the proportionality sign and you put there the proportionality constant. We can use K as a proportionality constant. It is fine. Okay? So you put it there, you say pi equals Kc. When we make K to be the subject of the formula, what do we get? We get pi divided by C, which is the concentration. Okay? So, however, we have that concentration is inversely proportional to volume. Okay? So we shall say C is equal to, if we remove the proportionality sign, we find that C is equal to K over V. C is equal to K over V. And when we substitute for C, we shall get that expression. And someone will ask, why do we get that expression? You know, I understand some people are not doing mathematics, pure mathematics, but this is simple mathematics, which you did even in O level. So when you have pi over C equaling to constant, okay, and you are applying that C is equal to K, small k over V. So how do you bring this one here? Okay, what you do, you put pi divided by K over V. So this one will be equal to pi times V over K. Okay? For those who are asking themselves, how is it coming about? So you get pi V over K is equal to constant. Are we together there? I think we are together. That is it. So if you go back to that slide, you don't say that you are confused. That is it. And we have always emphasized that we are dealing with A-level chemistry. The word A is not just, it is not just a letter, it is advanced. So you are advanced in each and everything. Okay? We're not going to be following these simple steps, saying this and that. Do them. Okay? You have enough time. Okay? The whole day. So get the slides, get a pen, get a notebook, start calculating all these things. Okay, practice. You'll be able to succeed. When we go to our next factor, which is temperature now. Now let us move to temperature and see how temperature. Then we shall say that the osmotic pressure of a dilute solution is directly proportional to the absolute temperature of the solution. Concentration, we said osmotic pressure of a dilute solution is directly proportional to concentration. And now here we are also saying is directly proportional to absolute temperature of the solution. So whatever we state, we have to explain why is it happening. Why is it that it is directly proportional? We see that the increase in temperature will increase what we call the kinetic energy of the solvent molecules. Okay? And therefore, molecules move faster from the solvent side to the solution side. Once you increase the kinetic energy, the solvent molecules will move faster. Okay? From where they are to where they are going. Okay? From the dilute solution to the more concentrated solution. This therefore requires a high osmotic pressure to force the solvent molecules back into the solvent. That's why we are saying osmotic pressure is directly proportional to absolute temperature, which is, we have now explained it, that you increase the temperature, osmotic pressure will also need to be high. You lower the temperature, the osmotic pressure, you find it very low. Okay? The pushing force should be equal to, the pulling force should also be equal to the pushing force. I don't know whether you have got that one. But since you are ready for learning and understanding, you have understood that one very well. I want to dot that one down. When we say, we have said pi stands for osmotic pressure, is directly proportional to absolute temperature. Okay? This is the proportionality sign. So when we remove it and put an equal sign, we shall apply the proportionality constant. So we shall say osmotic pressure is equal to Kt. K is the proportionality constant. I said you define all the terms you use. So here, when you make K be the subject of the formula, we shall find that osmotic pressure divided by temperature is a what? Is a constant. Okay, so we shall use this one also in one way or the other. So when we move to see how we can combine the two factors, how we can combine the laws, okay, to get one expression, and the expression for osmotic pressure, for determination of osmotic pressure, for determination of relative molecular mass of the solute. All right? So, yes, we'll say now we are going to combine the two. When we are combining the two, we don't combine the equations. When you combine this equation with this one, you're going to get something funny. Okay? What you combine the idea in them. You say that if osmotic pressure of the dilute solution is directly proportional to concentration and also directly proportional to absolute temperature, what do we get? Let's have a look at that. Please don't forget to visit our website and be able to access all this work. Okay? Visit our Facebook page. We copy all this information there. Code High School, Seta Bajo. Or you can contact me on my Facebook page, Saul Abooki. I'll be able to respond to you. So when we now go into combining the two factors, the two laws of osmotic pressure, we now say that they have said osmotic pressure of the dilute solution is directly proportional to concentration, and also directly proportional to temperature. So that's how we begin it. We say osmotic pressure is directly proportional to concentration and also directly proportional to temperature. All right? We begin it like that. We say that when we have a proportionality sign, we should remove it up and put there the proportionality constant with an equal sign. All right? So we say osmotic pressure is equal to K constant, okay, Ct. Are we together there? You have K, Ct. But remember, we are just from saying that concentration is equal to, if this is capital K, we shall say concentration is equal to small k over V. That's what we are from seeing, right? That's what we are from seeing. And now what happens? You will find that you are going to apply the two here. Okay? You are going to find that you have pi equaling to capital K, small k, T over V. However, we are dealing with the gaseous molecules. Okay? We are dealing for the gaseous molecule, okay, if you can say that, we find that this capital K and small k will be equal to what we call R. And R is the gas constant. I know most people here, they skip this step. Let us see what we get here. We get, if we multiply V here, we get pi V is equal to RT. Okay? That is the expression we get. Most people don't do this. They do this. They say, if we can begin from equal sign, is equal to CT. Okay? KCT. Osmotic pressure is equal to KCT. Is equal to concentration and times the temperature. So, most people, what they do, they say C is equal to 1 over V and come and put it there. Is equal to K T over V. Okay? They multiply it this side. They multiply this one this side and say it is pi V is equal to KT. Once they have that one, they say that they say that K is equal to R, which is equal to gas constant. And they substitute and they get this expression. Either way it is correct. You can apply this or apply this. Alright? It will still give you the same thing. Pi V is equal to RT. And this one is only for when it is 1 mole. 1 mole of a solute. When it is 1 mole of a solute. Here, when n equals 1. But for n moles of the solute, we will have pi V equals nRT, and here you say n equals number of moles of the solute. Okay? For n equals 1, we shall have this one. For n number of moles, we shall have this expression. Alright? And when we have that expression, we have almost attained everything. Okay? We have almost attained everything. Let us go to our slide and we emphasize a few things. There are some things we need to emphasize. More so, the SI units. The units we are going to use. They are very important. You cannot, you not just use anyhow these units and you'll be able to get the correct answer. So, next slide. For n number of moles. No? Yes, we continue and get the final expression. That slide is showing you what you have been doing on the blackboard. Okay? So on our next slide, you are going to see how we use it, what symbols do we use, and what units do we use and where. On our next slide. Okay? So you find that if V is in meter, okay? If V is in meter, we shall use the value of R as 8.314. Okay? If V is in decimeter, we shall use the value of R as 0.8314. Okay? If we have those ones, let us see what is there. We have the expression as NV equals RT. And we are saying that one is only for when N equals 1. Okay? That is when N equals 1. Let us look at our next slide. That one. Okay, so you can see that when n number of moles, we look at them, we get that expression. And that's what we have got on the blackboard. Okay? And if we have V in meter cubed, we shall have R as 8.314 joules per Kelvin per mole. Then pi should be in meters, in Newton per meter cubed or per cubed meter. Temperature should be in Kelvin. Okay? So, but when you go down and we see that V is equal to decimeter per decimeter cubed, you find that one pi is going to be in atmosphere, T is going to remain in Kelvin, and R will be in, it will be 0.8314 atmosphere per liters. Okay? Or atmosphere liters. Okay? So that's what you're going to be having if things change. Okay? So before you start calculating, before you start putting their values, you have to first look at the units of the volume. They are going to determine which R are you going to use. Okay? And they are going to also determine the units of the osmotic pressure at the end. Okay? Remember, there is a mark, a half mark for units. So what you see down, we say that equation down, pi v equals nRT, is what most people term to be the Van Hoff equation. If they say prove the Van Hoff's equation, please be able to follow those steps and you come up with that equation. And holds for only daily solutions. This holds for only daily solutions. For more concentrated solutions, it might not work for you. So let us look at limitations. Limitations have been emphasizing them, but majorly in this one, we have to say that the solute should be non-volatile. The solute should not, there should be no association or dissociation. In the beginning, we looked at association and dissociation. Association, you create more, you create a few from the big number. You reduce the number by grouping. Dissociation, you disorganize the groups and create large numbers. The temperature must not be too high or too low. We have looked at the effects of both. Okay? The solute must have a high relative molecular mass. Those are the limitations. Let us look at example 1 and we see how we can apply our equation of the equation we have got into that calculation. And so we shall have achieved our objective today, the second objective. We look at the question is saying at 25 degrees Celsius, that is the temperature now, 19.15 gram sugar was dissolved in 10 cube decimeter. Okay? Decimeter cubed of solution. Determine the relative molecular mass of the polymer. Determine the relative molecular mass of the polymer. What do you do first? We have said that once you get the question is having 25 degrees Celsius. That means you have to convert those ones into Kelvin. The question is having 19.15 gram of sugar. That means that is the mass. You should use that mass to get its number of moles. Okay? Then they are saying determine. Sometimes they can give you the RFM of the solute. Okay? So the RFM was given at 300. If we go to our next slide where is solution, the RFM was given, indicated properly in the question, but was given 342. Can see it. We have said temperature 25, you add 273, you get 298 Kelvin. Volume, it is there. R, I have said that once the volume is in meter, you use R. That means you have to, if you are going to use R as that one, please endeavor to convert the decimeter into meters. But it is very good if you put your mind into one direction. Always use meters. So whenever you get any volume in another unit, convert it into meters, so that you be safe and use 8.314. Okay? You can see, you get 10, you'll be able to get the value. So when you bring the expression, that expression we want to calculate for pi. Let us see here. When you have this and you want to calculate for osmotic pressure, which is this one, so that means pi will equal to nRT divided by V. So in this one, we're going to use this one. We are going to say pi is equal to, which is the osmotic pressure, is equal to nRT divided by V. That is simple mathematics. So let us go to our slide, and now we shall see that you calculate for number of moles, you get them. What is remaining is just substituting. Back to that slide of calculation. What is remaining will be just substituting. Okay? So let's go back to the slide of the calculation. That one. Once you have all the values, you just substitute. I have said 10 decimeter cube, you convert it into meters. You get 1 power -2. Okay? Then you substitute, you get the value, which is 138744.032 Newton per meter cubed. Take note, to apply the first principle method, okay? To apply the first principle method on the osmotic pressure, we need to use the standards, okay? I want you to take note of that. On our next slide, for you to be able to apply the first principles, you need to use all the standards. That means you need to use 1 mole of a solute in 22.4 decimeter per decimeter cubed, okay, at 273 Kelvin, causing osmotic pressure of that one. The increase in concentration increases the osmotic pressure, and when decreased, the osmotic pressure also decreases. We have seen that one. Let us look at an activity on how to apply the first principle. Okay? That activity, we want to use it to apply the first principle. Calculate the RMM of sucrose if a solution containing 19.15 gram of solution per decimeter cubed has an osmotic pressure of that one at 20 degrees Celsius. So you can see that we have been given the mass, okay? We have been given the osmotic pressure. We have been given the temperature. They want the RMM. If we are using this one, we are going to substitute. Remember, when you have N is the number of moles. N is the what? Number of moles. If you can focus here a little bit, we shall see that once you have pi V equaling to N RT, and N equals mass over relative molecular mass, okay? So we shall bring that one and substitute it here and say pi V is equal to RT times M over RMM. If we make RMM to be the subject of the formula, it will be equaling to M times RT over pi V. Are you seeing that once you have a general expression, you can play around with it to get the values, okay? Once you have this, you can use it. You say that number of moles is that one, pi v is equaling to that one. RMM is equaling to that. Okay? So that is it. So we can use this expression to get the right answer. I want you to use that expression to get the right answer. Since in the question you have the mass, it is there, 19.15 gram. You have the what? The osmotic pressure, which is 136,300 Pascal. You have the temperature, okay? You have the volume as 1, okay? So you should be able to get the right answer. 1 decimeter cubed, okay? Can note it, 1 decimeter cubed. That means that one will convert to meters, and you get 10 power negative 3 meters cubed, okay? 10 power negative 3 meters cubed. So once you have all that, you'll be able to get the right answer, okay? So during using this, I don't want to do much. I'll do less, you do much, okay? You do one number or two, you do all the numbers that you come across, okay? When you meet difficulties, you contact us, we shall guide you, okay? For us, we are just there to open the door, and for you continue moving, all right? So let us look at activity 2, and you note it. Activity 2 is there. At 25 degrees Celsius, the osmotic pressure of a protein contains 1.35 grams in 100 centimeter cubed container, as found to be 1216 pascals. Calculate the molecular formula of a protein. All those activities, they are yours, okay? You do them. Then let us look at that slide showing more activities so that can be captured in the video. For you, you can get the video, okay? You'll be able to do all those activities. That activity is there. Finally, you should go and read about effects. Next slide. Effects of dissociation. Next slide. Effects of, no, back, that one. Effects of dissociation and association of solids on colligative properties. Alright? So that is it that we can look at today. If you can go back to our slide 3 and you give that email, slide 5. It's okay. All of you have the email, visit the email and be able to access everything. You have been good listeners or good viewers. So let us meet next week to be a different segment. Thank you.